Welcome, I'm Chris Halliday from PowerLogic. We're a small company that operates out of New South Wales at a tiny little village called Gladstone. I've been in the industry for over 45 years now. It seems like only yesterday I started. I've been specialising in electric incident investigations now for somewhere around 20 years, but had been involved in a lot of investigations prior to that as well. We've got a few stragglers still logging in at the minute, but I think we'll get started. It's a short and hopefully sharp presentation, and I'll leave quite a bit of room, hopefully, for questions and answers. So I'll get started. These are the topics we're going to talk about. I threw in legal on top of what I mentioned originally. I just need to set the scene a little bit for investigation. So we'll get into those. First and most important legal issue, if we do have an incident, is to make the site safe and prevent any further incidents. And legal requirement with an incident is to notify the relevant authority. And then the third legal issue for an investigation is around evidence preservation. So we must preserve the evidence, but if the evidence has to get disturbed to make the rescue, then so be it. The rescue is the most important part, more so than preserving the evidence. But having said that, if there's two options, one is just as quick as the other, but one doesn't disturb the evidence, well, that's the process we should take. Item is we have a legal obligation to work de-energised. And that came into play around 2010 with the introduction of the new work health and safety harmonised legislation right across Australia. So even in our incident investigations, we should be looking to do our investigation with everything de-energised. And of course, the main purpose for doing an investigation is to prevent further incidents. And whilst the legislation in some states might not specifically lay out that we need to investigate an incident, we've got general work health and safety requirements for the safety of our workers. And so we need to take every opportunity to learn from our mistakes, and an incident being a mistake, if we can call it that. So some traps for the inexperienced. One of the main things is that incidents can be very daunting, particularly if the deceased person is still on site when you turn up to start your investigation. So that can be very daunting and threatening. The next two items tie in together fairly well. So ignorance, what don't you know? And that makes it very hard to do a professional investigation. Even our one-day electric shock investigation training course has positioned many of our clients in a reasonably good position moving forward. What I see is where non-electrical lead investigators take the lead role and don't listen to their electrical people. Yeah, not a good idea. The electrical experts need to be involved. And if you're ignorant, one of the things that can happen is you can leave the site unsafe. And I remember I had a phone call from one guy at one stage, and he told me about an incident he just investigated, and he was an hour and a half away, and I sent him back to the site to recheck something, and sure enough, he'd left the site unsafe, unbeknownst to him. The lack of technical expertise can focus on lots of areas, understanding of test instruments and the effects of current on human beings and livestock, and we'll talk a little bit more about those shortly. Some of you will have done my training courses before, and I'll be harping on about some of the same old stuff. One of the problems for the inexperienced is not having a process to follow. So having some procedures and perhaps forms to record your information is a good idea. And then, of course, training in those procedures so you stay on track and know what you're doing. There's also that many types of incidents that occur. It can be difficult to have your head around all the various types of incidents that occur. I had a phone call last week about an incident, and it was something I've never seen before in my whole career. So the variety, the types of incidents, the types of injuries can vary considerably. Trap for the inexperienced is you turn up on site maybe sometime after the incident and conditions can have changed. So you need to consider that. I investigated an incident 12 months after the event, way too long. The purpose was to collect evidence, but most importantly, to make sure the site was safe, even though it was 12 months later. Moving on. We'll have a look at some technical issues on this slide. And this graph is out of the Australian standard on the effects of current on human beings and livestock, AS NZS 60479 Part 1. And along the bottom, we've got current through the body starting at 0.1 of a milliamp and moving up to 10 milliamps, or 10,000 milliamps or 10 amps. On the side, we've got the duration through the body, starting at 10 milliseconds up to 10,000 milliseconds there, or 10 seconds. So the graph's divided into 4 different areas. Each area has a different effect on the human body, and it's for a current pathway, left hand to feet, and our 50 hertz system fits in. So in AC1, perception's possible. AC2 zone, involuntary muscular reaction, but generally no harmful effects. AC3 is this funny shaped zone, strong muscular contraction, difficulty breathing, immobilisation may occur, effects increasing with magnitude. So we could actually immobilise someone, such as with a gun as the police use. Yeah, and moving into AC4, cardiac and breathing arrest, burns, ventricular fibrillation, and the risk increasing with magnitude and time. So AC4 is subdivided into 3 different zones. In zone 4.1, there's up to 5% chance of ventricular fibrillation. In zone 4.2, up to 50% chance. And in zone 4.3, a greater than 50% chance of ventricular fibrillation. 3 values of importance here, and I always tell my students, if you learn nothing from my course, remember these 3 values, and I come back a few years later and they still haven't got them locked in their head. But anyway, the threshold of reaction is 0.5 of a milliamp. So if we touch something, get half a milliamp through our body, we'll start to react, and generally we pull away. At 10 milliamps for adult males, we're on the verge of locking on. So we've got hold of something, we can grip it, we'll be locking on about 10 milliamps. Ladies and children are something slightly less than the 10 milliamps. Drop down from the edge of the fibrillation area, or AC4 zone, we drop down somewhere between 20 and 50 milliamps. For left hand to feet, it drops exactly on 40 milliamps. But for other parts, other current paths, that can be slightly less than 30 milliamps. So our RCDs, our 10 milliamp RCDs stop us locking on, and our 30 milliamp RCDs stop us going into fibrillation. Okay, so lock those values in. 0.5 milliamp, we react. 10 milliamps, we're on the verge of locking on. And 30 milliamps or thereabouts, we're at risk of going into fibrillation. And if we transpose that into voltages, say someone's in a saltwater pool, they're swimming, and they contact something live, and their general body is in the general mass of water, perhaps somewhere around 5 or even less than 5 volts, the person could lock on. Now, the big risk with swimming pools in particular and swimming is once we get strong muscular contraction, our arms won't work, our lungs won't work, and we drown. Not very much voltage, and we could drown in a swimming pool. On series circuit, a little resistor in series with a big resistor, and you can see the big resistor gets most of the voltage. And this is particularly relevant when we're using a high impedance multimeter. So our high impedance multimeters are typically 10 million ohms, 10 megohms in internal impedance. Some might be 5 megohms, some might be 2 megohms, but typically they're 10 megohms. So if this is 10 megohms for our multimeter and we have a bad connection in series with our meter, say 10,000 ohms, our meter is the big resistor, so it will read most of the voltage. So just understanding that about a multimeter can make a big difference in its use. You know, taking measurements with a high impedance meter for electric shock incidents, the results are fairly meaningless. So we'll have a look at how to get around that shortly. The investigation process needs some pre-planning. We need a procedure to follow, forms, perhaps a report template when we get to the report writing stage. We need trained people, we need equipment, and some evidence storage facilities in case we need to confiscate some evidence. Incident, our first response will be important. Initially, we might do a mental risk assessment, and we need to make the rescue and secure the scene. Collecting all the evidence will be important once the shock victims have gone off for medical treatment, and all shock victims should seek medical attention. The heart rhythm can be mucked up, and people have been known to die a day or so after an incident. So important people seek medical attention. Collect the evidence, so there'll be a need for interviews of those at the site, photos, video, electrical tests, sketches, and collecting any items or evidence that we need to. Once we've collected all the evidence, and that's not always easy, even for experienced investigators, we'll need to analyse and interpret the data, and some of the analysis and interpretation is done as you're collecting the evidence. You know, one electrical test will lead to another, and so forth. One of Things we need to do is develop a sequence of events, important aspect, and then we get to the stage of doing our report writing. Depending on who you're working for, the type of report that you'll write. If you're working for a company where the incident occurred, you'll be looking to prevent further incidences and perhaps defend yourself in court. If you're working for the safety regulator, you might be looking to prosecute the company involved. So different organisations, different viewpoints. And once we finish the report, we need to make sure that all the actions in our actions plan are completed. We might like to do a post-investigation review. It's always a good idea. And you might want to consider counselling and sending off your report to the regulator, depending on the report that's required by the regulator, with what you'll send to them, and making sure all records are updated. Quite a lot of equipment that can be used. So these are all, most of them are fairly handy tools. I like proximity testers, very handy tools. Your multimeters, tester or a loop tester, loop impedance tester, an earth reel, so you can get out in the general mass of ground and determine which item is actually alive, whether it's the floor is alive or whether the piece of equipment might be alive, for instance. You can also use a logger to log shock voltages on pieces of equipment and also measure your neutral to the general mass of ground, the voltage across there. So use the logger to verify that you have solved all the problems, or perhaps where you've got an intermittent problem that you just can't nail down. So loggers can be a very useful tool. The shock investigation kit manufactured by CIC Australia. So there's various devices there, and 3 of them simulate the human body, working on a 2000 ohm person at 50 hertz. For higher frequencies, that resistance comes down. So just a rough rule of thumb, we use 2000 ohms for a person's body impedance. Now, the next 2 pieces of equipment are US-based pieces of equipment that do the same job as the Australian version. Which is better? I'm not quite sure. And lastly, we have the stray voltage eliminator. Some multimeters have this inbuilt into the meter as a low Z range. Now, these aren't suitable for electric shock investigations. They do not simulate the human body. They have a variable impedance just sitting there with no voltage on it. It's somewhere around 3000 ohms. Liven that up at 230 volts, and the impedance of the device, or the resistance of the device, is somewhere around 60,000 ohms. So the device is often incorporated in various meters. Okay, and regardless of what piece of equipment you use, it's always a good idea to understand the ins and outs of how that instrument works. What's the good, what's the bad? Your high impedance multimeters can be really good, or it can be really bad. Your proximity test, understanding that how they work is important. They're only a AC device. They don't work on DC, etc., etc. A few industry misconceptions. So one that I often hear is current takes the path of least resistance. You'll see the little circuit on the right here. We've got a 10 ohm resistor across 230 volts. Now, if I was to put a full hand around this conductor and get large area contact, one hand here, one hand here, let's say I'm 2000 ohms. I'm the large resistor in the circuit. So if this statement was true, all the current would go through here and I'd be safe as can be. Now, we know that's absolutely stupid. You put your fingers across a strong 230 volt supply and you will be electrocuted. So we can forget about this first statement. The next one, you often hear of surges. You know, I used to have people ring me and say, we just had a blackout and we had a massive surge. If you just had a blackout, how can you have a surge? This term is generally related to surge protection. I'm quite happy to use it for surge protection, but it holds no relevance in the electrical industry. We have lightning transients, impulsive transients from lightning and switching, load switching. They are not surges, they're impulsive transients. So I don't like the word surge. What I often hear is the largest resistor in the earth past is the ground itself. Well, that's incorrect. The ground's got so many parallel paths that it's a huge conductor. Our biggest problem is trying to connect earth electrodes to soil particles. And it's not like bolting two bits of metal together. We don't get such a good connection. And the soil around our earth electrode for a few meters or so, that's where most of our resistance in the earth path is, not in the general mass of ground. The general mass of ground is a huge conductor. This conception I see is that the RCD test button works the mechanism only, the trip mechanism. Well, that's incorrect. The RCD test button works at twice the rated residual current rating. So if you have a 30 milliamp RCD, the test button should operate at around 60 milliamps. Misconception is that lightning doesn't strike twice in the same location. Even one strike is made up of multiple strikes. So again, that's not correct. In summary, it's a great idea to understand your legal responsibilities when an incident occurs, and it certainly pays to be prepared. Follow your process that you establish for an investigation. Use your tools and equipment at hand, but understand their pros, their cons, how to use them, etc. I've included this little picture here of a cost-benefit analysis. That'll also be important to include in your report. You know, you could spend $1 million or $2 million to fix an incident. Is there ways that we can fix it to a reasonable standard and limit the expense? So certainly a cost-benefit analysis will come into play. And again, just to finish up is to be prepared. So I just wanted a quick presentation and then, oh gosh, I've took best part of 25 minutes, but have we got any questions? Let's see. Takes all paths was a comment from Daniel that works with me. Okay, Tony's asked about the emerging shocks from solar, battery, EV charger systems in the network. Tony, I haven't heard of many of recent times. The initial shock incidents that I heard about were in the early days of panels where earthing of the panels wasn't required, and you'd get some high frequency coupling onto the outside of the panels based on how the inverters were using the current. So I haven't heard of any recently. More modern times, we earth the panels, that gets rid of that. And I haven't heard any around charging systems or batteries. I guess they'll start popping up at some stage, perhaps with the home handyman scenario. Yeah. Okay, anyone else? Okay, I thought we might have got a lot more questions. Okay, I've left you stunned, or you're not going to speak up. Okay, hopefully the session was of interest. One just came in, or a few coming in now. Michael Bate, do you get more chance of shocks when the ground is dry? Oh, good question. Certainly it increases the resistance, reduces the current, but increases the shock voltage. Not sure on that one, Michael. Depends, I guess, on the situation. Tony Palladino, do you think RCDs have saved lives? Absolutely. Any electrician going to a switchboard, whether it be a main switchboard or a DB, and there's old style protection such as porcelain fuses or circuit breakers, we should be looking to upgrade those. Yeah, it comes at a cost, but then what's the cost of a loved one? Getting a few thank yous, comments. Investigator was to have one piece of equipment. What would you suggest? Thanks, Len. I guess you need a voltmeter and a shock kit. I do love my proximity tester though. Every good electrician should have a good quality proximity tester. Yeah, I guess you got to have a voltmeter to prove dead or prove isolated. Arrays, isolators no longer required. I'm not sure that's right. I'd have to verify that. They're only there for the emergency services. I don't know how many ever get used, whether it's too late by the time the fireys get there to use the isolator. I'm just trying to get through as many questions as quickly as I can and try and give some answer. Do you think arc fault detection devices will play a part in electrical safety to people, not just prevention of fires? Oh, they're all about preventing fires, Len. They're on domestic circuits typically, maybe commercial. They're more about preventing fires. I think a good step forward. Not that we, and I have written on this topic before. Not that we have a stack of electrical fires. That probably needs some clarification, but I think it's on our blog, on our website, if people are interested in reading about that. But RCDs too. I know I'm deviating from arc fault detection devices, but I'm of the opinion we probably should go to type B, and if we're all using type B, they'd probably be as cheap as type A or close there too. But and then we're protected for all types of loads. Okay. Robbie Nichols says that there is an option not to use. I guess he's talking about isolators. So, I haven't read that section of the new standard. So, bit of a flurry of questions then. We're up to 3:30 by the looks. Any final questions? One final one here from Mark Sims. Attended an incident recently where an employee received a shock from a switchboard. The board was shut down and retested. No issues were found. They claimed it was static. Oh gosh, I hate that one. It's much better to find something and feel confident about it than that. I know in salty environments, near beaches, switchboard protection devices can get covered in salt, and you can get a low current shock through that thin layer of salt. Yes, static's always a tricky one to find. It's whether they got the shock when they earthed themselves to the metal box, or whether they got it off a component. So if they got it off the box, it'll certainly pay to do some testing with a voltmeter, the shock kit, and the remote earth. You could, I guess, open the box with an insulated glove and shut the box down and then do your testing de-energise. Probably if they got the shock off the outside of the box, I'd be using not touching the box, but using a voltmeter and remote earth and the shock kit and see what voltage is on the box itself. If you've got any questions, go to our website and you can certainly email us. Last one from Tony Palladino: is there still a macho approach to electrical work by electricians? Well, I think there is, but it needs to be gotten rid of, Tony. We need to take electrical safety a lot more serious than we have in the past. Probably the biggest impediment to electricians' safety is themselves, and thinking that it's okay, say, to tighten up a loose screw or replace a circuit breaker while the rest of the switchboard's alive. We've got to get it into our bosses' heads and into our own heads that outages are required for even the basic little tasks that we might have done years ago live. Thanks, everyone. Catch you later. Bye.